Hey, fourth graders. Today's lesson I think is so interesting. And what I hope will happen is that after you watch these videos that you're going to want to look up more information about this after we get done with what is provided for you in the packets because it is so interesting. I've already learned so much just preparing for this lesson and I think it is super cool. So, in the description part on the YouTube video, I will include some other links for either other videos you could watch or some lessons that you can have more activities to do. Because those of you who love math, I think you're going to find the math piece of this very interesting. So, I want to start off by asking you, how many of you have just sat and looked at a flower before? The inside of a flower. I love this time of year. It is spring. Everything is blooming. I mean, your allergies might be kicking as well, but there's just so many flowers. And since we've been, kind of stuck in our homes, I've been walking around in my neighborhood a lot, and my neighbors have flowers. So I've been looking for different flowers around the neighborhood, and I like to take pictures of them. But this is a daisy, and so I just want you to notice, if you haven't before, the way the petals are arranged. It's almost like there's two layers of them. You've got this outer layer here, and then you've got an inner layer. And then in the middle of the daisy, it has the yellow parts, and it's in this pattern that actually makes a spiral. It starts really tight in the middle, and as it goes out, it spirals around and gets bigger. They're spaced out bigger. So I want to show you a couple other examples because these are going to be mentioned in the article. So I want you to be thinking about this before we read and have a mental picture of what some of these flowers and the patterns look like that the article is talking about. So can you tell what this flower is? It is a sunflower, and it's even got some bees hanging out on it. But the same thing with the sunflower is that these parts in the middle, they start out tight and then they spiral out. And actually, there are two different directions of spirals. You've got some this way, and then you've got some going the other way as well. And we're going to watch a video, and it's going to tell you more about that pattern. Another example of how you can see this sequence, and it's actually called the Fibonacci sequence, named after a mathematician whose name was Fibonacci. This is a succulent, and it starts out tight in the middle, and it spirals out and expands with more space. And in a pine cone, the way pine cones are designed, you've got this spiraling pattern as well. So I'm going to show you the video. And in this video, the guy presenting goes through these math equations really fast, and he talks about some things in math that you maybe haven't learned about yet, and you have no idea what he's talking about. And that's okay. I just want you to see what he says about Fibonacci and how he points out the patterns for the spirals in the flowers and in the pine cones. And the math part he talks about, it's okay if you don't understand it, but for some of you, you may want to look up the golden triangle and the golden sequence that he talks about later. You might find that interesting. So we'll start this.
How fast does a colony of rabbits grow, assuming that, well, they breed like rabbits? If mature rabbits produce a new litter every month, at first you'll have just the one pair, then two, then three, and then 5 pair as the offspring start having litters of their own. Soon the colony is growing fast, 8, 13, 21, 34, and then 55 pairs of rabbits. These are the numbers of the Fibonacci sequence, named after 13th century Italian mathematician Leonardo of Pisa, better known as Fibonacci. He introduced the rabbit problem about 800 years ago. The sum of 2 consecutive numbers in the Fibonacci sequence gives you the next number. Of course, real rabbits don't breed so predictably. But surprisingly, the Fibonacci sequence is common in nature. Look at the head of a sunflower. It typically contains two types of spirals, 34 spirals in one direction and 55 in the other. 34 and 55 appear back-to-back in the Fibonacci sequence. Some sunflowers have even larger Fibonacci numbers, such as 89 and 144. Pine cones often display similar patterns with 8 and 13 spirals. Again, consecutive Fibonacci numbers. This can't be coincidence, and in fact, there's more math at play. For a growing sunflower, it's beneficial to push out each new floret as far as possible from the existing florets. That gives each floret the most space to grow. Studies have shown that under many growth conditions, each floret should emerge at an angle of 137.5 degrees from the one that came before. Amazingly, 137.5 degrees is a well-known angle called the golden angle. It's famous for being derived from a number called the golden ratio, or phi. The golden ratio is closely related to the Fibonacci sequence. Take any number in the sequence, divide it by the one that came before, and voila, a good approximation of the golden ratio. So the golden angle produces the most efficient use of the sunflower's limited space, and the relationship between the golden angle, the golden ratio, and the Fibonacci sequence is what causes the sunflower spirals to appear in numbers straight out of Fibonacci. As beautiful as the sunflower is, isn't it even lovelier knowing that there's a deep mathematical order to it? For Scientific American's Instant Egghead, I'm John Matson.
So I really like that last part about there's a deep mathematical order to something that is so beautiful. I think that's very interesting. He starts out talking about rabbits in the beginning because that's actually what got Fibonacci onto this sequence. Is he was looking at rabbits and how they had babies, and so there was a word problem about rabbits and having babies and how fast they multiplied, and so that's why he started out this video talking about rabbits. So I would like you to get your packets or pull this up online. This is the article that we are going to read. And I don't know if you've looked through it yet, but if you were paying attention, there is a big typo down here at the bottom. It says petroglyphs, comprehension questions. And we know that we did the petroglyphs last week with Miss Morrow. So that didn't get changed. And also, don't always believe the answer key, because I'm going to tell you right now that the answer key is not correct. So we're going to go over that here in a little bit. But we're going to look at the questions first so that you know what to be thinking about as we are reading the article. So the first question what would be the best summary for this article? And remember, a summary is a short way to tell about what the whole article is about. We want to summarize it and keep it simple, but be able to express the main idea and the main points of the article. So, A, Fibonacci's dream was to develop mathematical equations that would explain nature. Sadly, in the end, his only real contribution was to change from the Roman number system to the Arabic. So my friends are texting about the electricity being out in Nashville right now. Thankfully, I still have electricity, and I can make this video. Okay, so another option for what is a good summary for this article is B. Fibonacci spent many years counting spirals in shells and petals and flowers, then made up an addition sequence that generated the numbers he had found. Or C. Fibonacci developed a mathematical sequence of numbers. We know now that the numbers in the sequence appear often in nature, while numbers not in the sequence do not. So we're thinking about what Fibonacci's discovery did and contributed to. Like, why is it important now? All right, number 2, what are Fibonacci numbers? A, numbers that follow a very specific pattern. B, numbers that are written as 1, 2, 3, 4 in Roman numerals, not 1, 2, 3, 4 in Arabic numerals. Or C, any numbers that can be found in nature. And number 3, you find a flower with 4 petals. Using information from the book, what could you infer? And infer means it doesn't tell you the answer straight out in the text, but based on what you know and based on what the text tells you, you can draw a conclusion and you can infer what it is saying. So can you infer that A, the flower is very rare and should be shown to scientists? B, the flower originally had 5 petals but 1 fell off? Or C, scientists have been incorrect about the relationship between Fibonacci numbers and flowers? Okay, so we are back at the article, and it is entitled Flower Numbers, written by Ivars Peterson and illustrated by Brian Taylor. Go count the number of petals on the flowers in your backyard, out in the country, or in a picture book. Did you notice that the number 5 keeps coming up? Buttercups, pansies, tomato blossoms, and geraniums all have 5 petals. So I wasn't sure if you knew what those flowers looked like, so I've got a couple pictures for you to look at on this PowerPoint. And these are buttercups. So if you see, there's 1, 2, 3, 4, 5 petals there. These are pansies, and 1, 2, 3, 4, 5 petals on pansies. And tomato blossoms, 1, 2, 3, 4, 5 petals on those tomato blossoms. And these are geraniums. Further away, like you might see these on people's porches or in their yards. This is what geraniums look like in a pot. And then up close, these are the geraniums. So it's harder to count them because they're red and they all run together. But it looks like 1, 2, 3, 4, 5 right here. And this is a picture of Leonardo Fibonacci, who we're going to be reading about in the article. So back to the article, and it says, you may also find flowers with 3 petals and others with 8, 13, or even 21 petals. But it's harder to find flowers with 4, 6, 7, or 10 petals, unless some have been nibbled by animals or insects. I'm going to give you a hint. This is helpful to answer number 3. Is there something special about the numbers 3, 5, 8, 13, and 21? As a matter of fact, there is. To see what I'm talking about, start with the number 1. Then add 1 plus 1 equals 2. Then add the 2 numbers on each side of the equal sign. Keep doing this and you get a pattern. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13 equals 21, and so on. This set of numbers, 1, 1, 2, 3, 5, 8, 13, 21, 34, goes on to infinity, like forever. There's no ending for it. They are called Fibonacci numbers. They are named after the mathematician Fibonacci. He lived in Pisa, Italy, 800 years ago. He was probably the greatest mathematician of his time. He was one of the first Europeans to use the Arabic number system. And it's the numbers that look like this, 1, 2, 3, 4, etc. Instead of the Roman number system, where you've got the I, IV, those are the Roman numerals. Fibonacci numbers show up all over nature. They are in spirals of pine cones and pineapples, in the swirls of snail shells, and in flowers and leaves. Why? It might have something to do with how plants and other living things grow. If so, math and nature work very closely together. So I'm going to stop the video here because I'm about to run out of time, and I will start the next video, and I'm going to show you some more pictures to explain some of the things in this article, and then we're going to do some work.